Okay, so today we're going to talk about section 4.4, which is other common functions. We want to learn how to evaluate and graph power functions, the absolute value function, the greatest integer function, and piecewise defined functions. We start out with the definition. A power function is a function of the form f of x equals ax to the r, where a and r are real numbers. So let's talk about power functions of the form a times x to the n for a minute. Let's look at example 1. In example 1, we want to sketch the graphs of the following functions and find intercepts, if any. G of x equals 2 times x squared. This is a parabola facing upward because this 2 is positive, and we know it's greater than 1, so this graph of 2x squared is similar to the graph of x squared, and the 2 means we stretch it vertically by 2. So this is what we get. Our graph is a little bit narrower than x squared. So part B says we have f of x equals negative x to the 6th over 4. Right now we're talking about power functions that have even exponents, okay? Now, a power function that has an even exponent is going to have this shape. It's going to have the shape of x squared. The only thing that's going to happen is it's either going to get flatter or it's going to get, we can press it down, which will make it wider or broader, or we can stretch it and it'll become narrower. Now, if we have a negative here, that means we flip it over the x-axis, okay? You can always, if you want to, plot a few points to help you. Would you like to see points plotted? Yes or no? Yes? Okay. So let's do that. So here you have, in your problem, you have x, and then you have f of x. So you have x and you have f of x. So if you want to take -1, 0, and 1, you can choose any numbers that you would like to. Right now, we're just trying to get an idea of what our graph is going to look like. So when x is -1, you substitute -1 here. So notice that you have that negative on the outside, and then you have times -1. That's a little big, so let me rewrite it. A negative on the outside, and then you have -1 to the 6th over 4. -1 to the 6th is 1. This is a positive 1, but you have that negative on the outside, so you end up with -1/4. You end up with -1/4. Okay? So when x is -1, you end up with -1/4. Somewhere here. Okay? When x is 0, what do we get? 0. Good. Because you'll have negative times 0 to the 6th over 4. But that's -0. That's just 0. Okay? So whenever you have 0, you have 0. So there you go there. And then when you substitute in 1, what do we get? You said what now? Not +1/4. Tell me why it would not be positive. It'll still be negative, right? Because that negative is right here. Because you have this negative right here still. Good. So you have the negative hanging out, but then you would do 1 to the 6th over 4. So this will give you -1/4. So you have 1, -1/4. And then you sketch the graph. And that's your graph. This is the graph of -x to the 6th over 4. What questions do you have? Okay. All right, so let's continue. Let's look at an example that has odd exponents. So you saw in the case of even exponents, the shape of the graph was similar to that of a parabola. It was that of a parabola, okay? Facing up, and in this case, facing down. Okay. Example 2. Same instructions. Sketch the graphs of the following functions and find intercepts, if any. Here we have d of x equals 2x to the fifth. D of x equals 2x to the fifth. So if you want to plot points, you have x, and then you have d of x. What values of x do you want to choose? Come on. What values of x do you want to choose? -1, 0, and 1. Good. Okay. So then we substitute these values in and we solve. So -1, we would have 2 times -1 to the fifth. What's -1 to the fifth? -1. Good. So we end up with 2 times -1, which is -2. Which means -1, -2 is a point on your graph. Okay? When you substitute in 0, you have 2 times 0 to the fifth. What does that give us? 0. Good. So that means 0, 0, where the origin is a point on our graph. Whenever you have x is 1, that gives us 2 times 1 to the fifth, which is what? 2. Good. So that means the point 1, 2 is on your graph. And you can continue plotting points so you can see the shape of your graph is going to look similar to this. That's the graph of 2x to the fifth. So no surprise, when your exponent on x is odd, this is going to be the shape of your graph. The end behavior is going to look like this. The end behavior is going to look like this. But if you have a negative outside, that negative is going to flip this graph and it's going to look similar to that. Okay, so make sure you work through your homework to practice these. Okay. So we've talked about power functions of the form ax to the n, where n was even and n was odd. So now let's talk about power functions of the form a times x to the negative n. A times x to the negative n. So remember, this is just a recall, not for your graph, but this is a recall because you'll see this interchangeably. So remember that if you have x to the negative n, that's the same thing as 1 over x to the n. X to the negative n is the same thing as 1 over x to the n. Okay? So when you're graphing f of x equals x to the negative 1, x to the negative 1 is the same thing as 1 over x using this rule. Okay? Now, to graph it, can x be equal to 0 here? No, because our denominator cannot equal to 0. Good. So we cannot have x equal to 0, which means you'll never touch, whenever you see the graph of this, it will never touch this y-axis because we cannot divide by 0. Okay? So here, when you're graphing this, you can plot points if you would like, but the general graph of 1 over x is equal to this. This is the graph of 1 over x. It will not touch the x-axis either. Okay? That's the graph of 1 over x. If you want to see plots or see points plotted, you have x, you have f of x. If you choose -1, 0, and 1, if you substitute in -1, or let's add 2 to that as well. If you substitute in -1, that gives you 1 over -1, which is -1. So 1 over -1, which is -1. If you substitute in 0, we get undefined, so that's not possible. If you substitute in 1, you get 1 over 1, which is 1. You substitute in 2, what do you get? 1/2, good. You get 1/2. So notice that the larger the numbers that you substitute in, your number is going to get smaller and smaller. This is why it's getting closer and closer to the x-axis, but it will never touch the x-axis. Okay? Questions? So no surprise that if you have odd exponents and you have a negative odd exponent, the graph is going to have the same shape. Then what's going to happen? Either it's going to get closer to the y-axis or further away from it. Okay? If you have x to the negative third, this is 1 over x cubed. Okay? So we're going to have, this is our graph. And we're just sketching. This is our graph. If you want to plot points, you can. If you want to see what's happening, you can plot points. You might want -2, -1, 1, and 2, because we know that we cannot have 0. So when you substitute in -2, you get 1 over -2 cubed. -2 cubed is -8, so you get -1/8. You get -1/8. So that means when you have -2 out here, you get -1/8 as your point. When you substitute in -1, you get 1 over -1 cubed, which will give you -1. When you substitute in 1, what are you going to get? When you substitute in 1, what are you going to get? 1, good. You're going to get 1. When you substitute 2 in, what are you going to get? One over what? 8, good. You get 1 over 8. 1 over 2 cubed. 2 cubed is 8. Okay, and then you could plot those points. So whenever we graph x to the -5th, that's 1 over x to the 5th, then this is your graph. Is it ever going to touch the x-axis? Is it ever going to touch the x-axis? No. The numbers are just going to get closer to the x-axis faster. Okay? You can also have power functions of the form ax to the -n, where n is an even exponent. Okay? Now, notice that the graph, before we move on, notice that the graph of ax to the -n, where n was an odd exponent, it didn't have the same shape as it did where you have ax to the n, where n was odd. It's important to notice the shapes of the graphs because you will see these often. Okay? So let's go on to even exponents. Using this recall in green, x to the -2nd is 1 over x squared. X to the -4th is 1 over x to the 4th. And x to the -6th is 1 over x to the 6th. You need to be able to go back and forth between these with ease. Okay? So, let's plot a few points here. Can x ever be equal to 0 for these? No, it cannot, because we cannot divide by 0. So, whenever we're graphing these, you can choose your x and your f of x. You have -2, -1, 1, and 2. You can choose whichever numbers you like. I'm choosing some negative and positive so you can see what's happening on both sides of the graph. Okay? So whenever you substitute in -2, you have 1 over -2 squared. That gives us 1 over 4. So when x is -2, your y value is 1/4. So if that's 1, 1/4 is somewhere around there. Okay? When x is -1, what do you get? I'm going to respond. When x is -1, what do you get? 1. Good. You get -1 because you have 1 over -1 squared. That's 1 over 1, which is 1. So you have -1, 1. Do you think the graph, whenever you substitute a -3, is going to get a point that's higher or lower? Lower. Will it ever cross the x-axis? No, it won't. So we can already go ahead and sketch this graph. We also know it will not touch the y-axis, right? Because we cannot have x equal to 0. So we already know the shape on the left side of this. No surprise, on the right it's going to have a similar shape, but mirrored across. So whenever you have 1, you have 1 over 1 squared, which is 1. When you have 2, what are you going to get? 1/4. Good. So you're going to have 1, 1. So that's the point 1, 1. Then you're also going to have 2, 1/4. And then you can sketch the graph here. Okay? So that's the graph of 1 over x squared. No surprise. It's going to look similar for 1 over x to the 4th and 1 over x to the 6th. It's just going to flatten out a little bit. Questions? Yes? So the question was, if you have x to the -2nd, why are we switching it in its format here to a +2? Because what we're doing is we're using this rule here in green. You have x to the -n. You can rewrite that as 1 over x to the n. So we're rewriting x to the -2nd as 1 over x to the 2nd. So whenever you write it as 1 over x to a power, that becomes positive there. What questions do you have?
We only use that for the negative ones, right?
Can't hear you.
We only use the recall for the ones with the negative.
Absolutely. You only use the recall for the power functions that have a negative exponent. If you need to send a text message or make a phone call, go out in the hallway and handle that. But yes, you only use these for negative exponents. What other questions do you all have? Okay. Functions of the form, power functions of the form a times x to the 1 over n. Okay. X to the 1 over n looks like an nth root. So the recall here is that x to the 1 over n is the same thing as the nth root of x. So for example, if you have x to the 1/2, if you have x to the 1/2, that's the same thing as what? The square root of x. Very good. That's the same thing as the square root of x. We know the graph of the square root of x. We've graphed that before. The square root of x has this graph. That's the graph of the square root of x. Okay? So that's an example. You can also have others, okay? You have to sketch the graphs of the following functions and find the intercepts, if any. Do you all remember the graph of the cube root of x? That's a question. Yes or no? No. Okay. Make sure you're reviewing. Make sure you're studying. Your exam is Thursday. Okay? So, an aside, the graph of x to the 1/3. X to the 1/3 is the same thing as the cube root of x. Okay? So whenever you're trying to graph this, and we're not doing those examples yet, we're just doing a refresher. So you have your x and your y axes. So let's call this our f of x. So if we take x values, we want to determine what f of x is. Okay? So if we have -8. If we have -8, then what's the cube root of -8? What's the cube root of -8? Say it again.
Is it 2i?
No, not 2i. That's a good guess. You're thinking I because you have a negative underneath. But you can think about it another way. What number cubed is equal to -8? What is it? Positive or negative? What number cubed is -8? -2. Good. -2. So this is equal to -2. So that means the point -8. So when x is -8, -2 is what you get. So the point -8, -2 is a point in your graph. Whenever you have 0, what's the cube root of 0? What's the cube root of 0? 0. Good. So that means the origin is a point. You can choose -1 too if you want. If you choose -1, what's the cube root of -1? -1, because -1 cubed is -1. Good. So -1 is a point on the graph. We can make that a little better. Okay? When you have 1, what's the cube root of 1? 1, good. When you have 8, what's the cube root of 8? 2, good. So notice that the graph is going to look like this. That's the graph of the cube root of x. So no surprise, when we have -1 times the cube root of x, this graph is going to be reflected over the x-axis, right? And it's going to look like that. It's going to look like this. That's the graph of -1 times the cube root of x. If you have g of x equals the square root of x over 2, notice that this is the same thing if you had it in this form as x to the 1/2 or 2. This is the same function. We can also rewrite this as 1/2 times the square root of x. The fact that this 1/2 is between 0 and 1, notice that for the square root of x, the shape of the graph is like this. Since this is between 0 and 1, are we going to stretch this graph or press it down? We're going to press it down. Very good, because it's between 0 and 1. So it has the same shape as the square root of x, but we're going to press it down. So this is going to be our graph. So for example, whenever you have x and g of x, if you want to find out when x is 4, that gives us the square root of 4 over 2. Square root of 4 is what? 2. Good. So you have 2 over 2, which is 1. Good. So when x is 4, you have 1. What questions do you have? Okay. Now let's talk about the absolute value function. Let's talk about the absolute value function. The basic absolute value function, is f of x equals, we write this as a vertical bar, x vertical bar. This is the absolute value of x. And the absolute value of x is defined as x if x is greater than or equal to 0, and negative x if x is less than 0. X, we know the graph of x is a line like this. So just do not graph yet. We're just discussing this. The graph of x looks like this, right? But it says it's x only if x is greater than or equal to 0, right? That means if x is greater than or equal to 0. So that means we have from here on out, which means we ignore this part of the graph, right? So this part is gone. Okay? Then we have negative x if x is less than 0. We have negative x if x is less than 0. The graph of negative x, we know, has a slope of -1 and looks like that. But the thing is, it says if x is less than 0. So only from here on out. But that means we do not need this part of the graph. So we erase that. This is the graph of the absolute value of x. That's the graph of the function, the absolute value of x. So you can take time and graph that. Okay, so this is the graph of the absolute value function. It's equal to x if x is greater than or equal to 0. It's negative x if x is less than 0. Okay, how many parts to this function are there? Say it loud. 2. We're going to talk about piecewise defined functions. Piecewise defined functions in a minute. This is an example of a piecewise defined function. It's a function that has multiple parts of its definition. Okay, this is an example. Okay, now, in our example, our next example, I ask you to graph the function g of x equals -1 times the absolute value of x. What is that going to look like? Do it again. I see you drawing it in the air. It's going to look like, is it going to look like a V? It's an upside down V. Why is it going to be an upside down V? Because it's negative. You're absolutely correct. So it's just like this. It's just like that. Very good. That's -1 times the absolute value of x. That's the graph. Okay? Excellent. Definition. The greatest integer function, f of x, and your book, it will have it like this. I just tend to write it this way on paper so you can see the difference. Okay? So, the greatest integer function, new function, f of x equals, it's written this way, is a function that's commonly encountered in computer science applications. The greatest integer of x, the greatest integer of x is the largest integer that's less than or equal to x. That's important. It's the largest integer less than or equal to x. Now, let's look at an example. Let's consider something here. If you have your number line, you have 0, 1, 2, and 3. -1, -2, and -3. If we have -2 that's a -3. If we have -2.9, that's somewhere out here. What is the largest integer less than or equal to -2.9? -3. Very good. -3, because it's the largest integer that's less than -2.9. So that's -3. Right there. If you have 4.4, what is the largest integer less than or equal to 4.4? 4. Good. 4. Remember, you're choosing the largest integer that's less than or equal to that. The fact that it's less than means you have to go to the left of it, not to the right. Does that make sense? Okay, so you get 4 here. You get 4 here. Okay, so whenever you sketch the graph, no surprise, whenever you have 0, you actually pick up 0, so that's a closed circle. Everything between 0 and 1 is going to be 0. And then you're going to have an open circle at 1. If you have 1.2, what is that going to be? The greatest integer less than or equal to 1.2 is 1. So no surprise, you're going to pick up 1 here. Everything between 1 and 2 is going to be 1 except for 2. If you have the greatest integer less than or equal to 2.5, what is that? What is that? 2. Good. So no surprise, this is what you're going to have. And we're going to keep going up in that way. Similarly, you can go down in this way. Some people call this a stair-step function. This is also a function that jumps. This is the graph of the greatest integer function, or the greatest integer of x. What questions do you have? Okay. A piecewise defined function, a piecewise, when you hear the word piecewise, what do you think? You think of separate parts or pieces? Good. A piecewise defined function is going to be a function defined in terms of two or more formulas, each valid for its own unique portion of the real number line. So it is what you think it would be. Piecewise defined means it's going to have more than one part where it's defined. Okay? In evaluating a piecewise defined function f at a certain value of x, it is very important to correctly identify which formula is valid for that specific value. Okay? So let's go through a couple of examples. I see some still writing, so I'll give you a minute here. Okay? So example 5. Given the following function, evaluate the function at the specified value or values indicated. And in the last part, we're going to sketch the graph. Okay? So let me ask you this. How many parts of P of X do we have? 3. Very good. You have x plus 1 if x is less than negative 2. You have x cubed if x is greater than or equal to negative 2 but less than 3. And you have negative 1 minus x if x is greater than or equal to 3. Is this confusing for anyone? Yes or no? If you're confused, you got to let me know. Otherwise, I'm going to keep moving. Okay? What? So this has 3 parts to it. It's x plus 1 if x is less than negative 2. X cubed if x is greater than or equal to negative 2, but less than 3. And it's negative 1 minus x if x is greater than or equal to 3. Okay? For those who are visual, you can picture this on the number line. I will color each part. You have x plus 1 if x is less than negative 2. So if you draw a number line, the points you mark on the number line are the numbers that appear on this side. So you can mark your negative 2 and what other number? 3. Good. If x is less than negative 2, notice that it says less than, so that means you have an open circle. If it's less than negative 2, then the function that we use is x plus 1. If we are between negative 2 and 3, notice that this is a less than or equal to, right? Which means this will fill the circle in. And it will go out to 3. At 3, will it be a closed or open circle here? Open, very good. Because it's strictly less than. So that means we have x cubed. We're not drawing the graph. We're just understanding the piecewise defined function at this point. We're not sketching the graph. We're just understanding the piecewise defined function. And then you have negative 1 minus x if x is greater than or equal to 3. So you have the green part. What happens at 3? Closed circle, so you fill this in and all the way to the right. Good. So the purpose of going through and doing this is because whenever you have to find P of a specific value, you need to know which part of the function you're in, red, blue, or green. So P of -5 means x is equal to what? -5. This means x is equal to, this means x is equal to -5. What part of the function are we in? Are we in part 1, 2, or 3 if x is -5? Part 1. Very good. So we're in the red part of the function. So we use x plus 1. So P of -5 is going to be -5 plus 1. I'm using the color to indicate what part of the function we're in. -5 plus 1 is? -4. So -4 is our answer. What questions do you have? Yes. Can you talk a little louder?
How come we can't use the other equations?
So the question was, how can we not use the other equations? Because -5, is -5 between -2 and 3? If we look over here on our graph, -5 comes in over here, right? That's why we're using this part. Does that make sense? Okay. For P of 4, where does 4 fall into? Equation 1, 2, or 3? 3. Good. 4 is over here in the green portion. 4 is over here. This means x is equal to 4, which means we use the green part of our function, which is -1 minus 4. -1 minus 4 is -5. Good. So we get -5. What about C? We've gone through A and B together. We've answered the question, what part of the function are we in? Then we evaluated it. So you explain part C to me. X is 1. Good. This means x is 1. Go ahead. We're using the second part of the function because you have -2 here and 3 here. 1 is here. Good. So then what? We have 1 cubed, which is 1. That's that. What questions do you have? You'll see this type of problem again. Okay, so now let's sketch the graph. To sketch the graph, you need to know the graphs of basic functions. Okay. Well, it's not doing it. So I'll use a similar color. Whenever you have x plus 1, typically, x plus 1 would typically look like go up 1, draw your line. That's what x plus 1 would typically look like, right? But we only want x plus 1 when x is less than -2. So whenever you go over to -2, you get -2 plus 1. What's -2 plus 1? -1. So that means -2, -1 is a point. Here, we have an open circle because this is less than. We only want this portion. Everything else goes away because we're strictly less than -2. So we only want this chunk of our graph. So explain one more time. This is your graph of x plus 1. But we only want the graph whenever x is less than -2. So from here on down. So we have an open circle here because that's less than. And that means we ignore everything else up here. So that's why we only want this portion. Okay? Now for x cubed. We know what the graph of x cubed is. The graph of x cubed looks like this. That's the graph of x cubed. But we only want x cubed when x is greater than or equal to -2 or less than 3. Less than or equal to -2 means it can be equal to -2. -2 cubed is what? Positive or negative? Odd exponents, if you have a number raised to an odd exponent, it's going to be negative. If it's an even exponent, then it will make that positive. So this is a -8. So -2, -8 is a point on the graph. Okay. Will the function ever be equal to 3 for this part? For the blue part? No, it will not, because it says it's strictly less than. So we can go ahead and sketch the graph. We know the graph looks like that. We know it's not going to be equal to 3 there. It's going to get close to it, but it won't equal 3. And then we have -1 minus x. So minus x looks like this. Minus x looks like that. Whenever you have -1, that means we drop this down 1. Can make it a little better. That means we drop it down 1. Okay? Again, if you need to send a message, go out in the hallway to do that. Okay? So, if you have x, notice that it can be 3 or larger. If you substitute in 3 here, what do you get? -4, good. So 3, -4. You're going to have a closed circle or open circle here?
You're going to have a closed circle.
Closed circle, good. Why?
Because it says equal to.
Good, because it says greater than or equal to. And that's the graph of your function. What questions do you have? So when you're going through your homework, you'll see graphs where you have to sketch it, or problems where you'll have to sketch the graph or match the graph. Okay, one more example. Take a few minutes and do parts A through C here. Given t of x is this piecewise defined function. It's x to the 4th if x is less than or equal to 1. It's the greatest integer of x if x is greater than 1. Evaluate t of -2, t of 1, and t of 7.9. I want us to do this first. So go ahead and take a take a couple of minutes, take 2 minutes, and do A through C.
Okay, for A is...
You hear in the back?
Oh, yeah, can I?
He said yes.
Okay, for A is T with the -2.
You can use your highlighter if you want. The pointer, the laser is here. Let me show you.
Yeah.
It's all good. You have it. This is your laser.
Mhm.
That's to write with.
Okay. So this, what I do
Yep.
with the laser?
If you just touch, point what you're doing.
Oh, okay.
So people can follow you.
Okay.
And this is to write.
Okay.
Tap that away.
Okay, so that's T, -2. And -2 is less than or equal to -1. I mean, less than or equal to 1. So use that equation, I guess. So it's -2 to the 4th. And that's ugly. -2 to the 4 would be 16. Positive 16, not -16, because it's negative. Y'all get that?
Because what?
Oh, I don't know how to explain that, but like -2 times -2
That's
would be.
explaining it.
Okay, -2 times -2 is 4. 4 times -2 is 8, and then -8. I mean, yeah, it's -8. -8 times -2 would be positive 16. That's how you get a positive 16, not a -16. And then this is T1 and 1.
Of one.
Oh, T of 1. And 1 is, again, either was equal to 1. So you'll use this first equation again. So then you get 1 to the 4th, which would just be 1. And then for the last one is 7.9. And that's greater than 1. So you would use the... Which one is that?
She's asking you all a question.
The greatest.
Oh, okay, yeah, the greatest.
Can I get the same kind of responses?
I don't remember the name of that
Good.
one.
They're responding to you.
Okay, greatest integer of x. You use that one. So, I guess I gotta write it like that. Ooh, that is ugly.
No, it works. Make sure you can read the decimal.
Okay, so greatest integer of x, and that would be 8, because it's closest to 8, right? Would it? It's 7? Sorry, y'all. I came late for that one. I'm sorry.
You can't read nothing. Listen, my rule is we always stay positive. So we always stay positive.
Okay, wait. Why is it 7?
That's right.
Can somebody tell me?
Because
This
it
is
has
why
to
we're
be
here.
the least greatest common.
Oh, okay. So it's not. You don't go up. You go down.
Right.
Okay. Well, I don't know how to erase, y'all. So just.
Don't forget
Erase.
erase that part.
Erase is the one.
Oh, I found it.
That's so funny.
Okay, I found it.
The greatest least.
Yeah, that's why I was confused. Okay.
So explain it again. So we have that explanation there.
Oh, okay. So we trying to find the greatest integer of x, and x is 7.9. So the greatest integer of x would be 7, because it's the least greatest integer.
You got it.
Okay. Yeah.
Okay. Very good. We applaud. You can pause it. Okay. So to sketch your graph, it's important to remember which part of the function goes with what. Okay. So if you want to use a color, x to the 4th, we use for red. X to the 4th, what's the shape of the graph? Excellent. It's a parabola, but that vertex should touch at the origin. Should touch at the origin. But the thing is, we only want x to the 4th if x is less than or equal to what? 1. So we go out to x equals 1. When x is equal to 1, what is y? 1. Good. Because t of 1 is equal to 1 to the 4th. You patting your head mad loud. T of 1 is equal to 1 to the 4th. That's equal to 1. So this point is 1, 1. Are you with me? Yes or no? That's the y, okay? We only want x to the 4th if x is less than or equal to 1. So what do we do with this chunk? We throw it away. We throw it away. We don't want it. We don't want it. Which is why when we're putting our graph together, we're only going to take the part that we want. We're only going to take that. And we ignore that. Okay? That gives us the x to the 4th portion. Then we want the greatest integer of x when x is greater than 1. So that means when x is greater than 1, we want the greatest integer less than or equal to that value. Well, between 1 and 2, we can use blue for that if you want. So here, it has a closed circle out to 2 here. But then whenever it's between 2 and 3, we move up. So this was 1, that was 2, then 3, and then you keep going. That's your graph. This is the graph. What questions do you have? Yes,
So.
there are 3 questions. I see you all. Go ahead.
For the integer part.
For the greatest integer function, you mean?
Yeah.
Uh-huh.
So it says if x is greater than 1. So wouldn't on the graph that first piece be missing?
Hold on. If x is greater than 1, so this is technically red. This piece would not be missing because so the question was, would this piece be missing? Is that your question?
Yeah, like would it be an open circle since it's not equal to it?
It would be open for blue. It would be open for blue, but for red it's filled in. And on your paper, you would be using black, right? So, or your pencil, which means this would just remain a closed circle from here on out. Here, you do pick up this piece because if you have 1.1, 1.1 would give you 1 because the greatest integer less than or equal to 1 is 1. And anything between 1 and 2 would give you 1. Okay? Shelby, you had a question.
Yes.
Okay. Zalia, you had a question.
Why do we start the greatest common integer at 1?
Why do we start the greatest integer function at 1? Because if x is greater than 1, that means we don't start at 2. We start as soon as you have a number slightly larger than 1. So 1.0005. That's greater than 1. That falls into this point, into this part of the function, which means we would still have something here. That's why we don't start at the next integer, we start in between. What other questions do you all have? Yes.
So that line means there's something.
Yes, that line means there's something in here. Yes. What other questions do you all have? Okay, so this concludes section 4.4.